The atom bomb to nonstick cookware, polytetrafluoroethylene, PTFE, more commonly known by the brand name Teflon, is a compound that has changed the world. The discovery of PTFE was entirely happenstance, the unintended result of investigations into the creation of a new chlorofluorocarbon refrigerant by the DuPont Corporation. During his investigations, Roy J. Plunkett noticed a discrepancy in the weight of an empty tetrafluoroethylene gas canister and opted to open the container to determine the cause. Within the container, he found a white, slippery, and waxy substance coating the iron walls. In its accidental 1938 discovery, steel acted as a catalyst under high pressure, but today, most PTFE production occurs by free radical polymerization of tetrafluoroethylene in a water suspension.
Teflon, or polytetrafluoroethylene, is a vinyl polymer and is made from the monomer of tetrafluoroethylene. The process of manufacturing it is actually through something called free radical polymerization. Polytetrafluoroethylene, therefore, is made entirely through a long chain of carbon backbone. The backbone could have thousands of carbon attached, meanwhile, each of the carbon in this backbone is bound or connect to single fluorine atoms via a covalent bond. The properties of fluorine is what make Teflon such an interesting polymer. Fluorine as an element is very strange, and in this case is very picky. It only prefers to be drawn to its own kind, and so it will even more likely to repel anything that is more other than fluorine. For example, like water. With the whole molecule of Teflon or PTFE being almost entirely made of by fluorine, it does not want to interact with any other molecules and tries to stay as far as possible away from anything else that tries to come in contact with it. Hence, nothing will stick to Teflon. The first step of making Teflon is synthesizing TFE. The three main ingredients for TFE include fluorspar, hydrofluoric acid, and chloroform. They are combined in a chemical reaction chamber heated between 1094 to 1652 degrees Fahrenheit. The resultant gas is then cooled and distilled to remove any impurity. An important thing to note is that special apparatus like preventing hotspot are needed for polymerization of tetrafluoroethylene because the decomposition of it to carbon and tetrafluoromethane can be very explosive. The initiation of this polymerization process is typically initiated with persulfate, which hemolyzes to generate sulfate radicals. The resulting polymer is terminated with sulfate ester groups, which can be hydrolyzed to give OH end groups. PTFE is poorly soluble in many solvents. Therefore, the polymerization is conducted as an emulsion in water, and this process results in the suspension of polymer particles.
The Manhattan Project, a program to develop and produce nuclear warheads during the Second World War. The researchers and engineers found that the seals and gaskets were eroding rapidly, could not handle the challenging environment imposed by weapons-grade uranium hexafluorides. Thanks to polytetrafluoroethylene's resilience, its ability to be chemically inert, and low coefficient of friction, it ensures that it was the perfect candidate for handling the rigors of being a gasket or a seal in a nuclear warhead to ensure that no harmful gases are released during any part of the process.
Now let's talk about the downside of Teflon. As stated, Teflon is non-toxic, but the process of producing it would produce byproducts that are like hydrofluoric acid and carbon dioxide. In the process of PTFE production, the work environment always has to be adequately ventilated during the heating or sintering process. Workers that are directly in contact with the product can get something called polymer fume fever because of constantly inhaling the toxic gaseous byproducts. The leftover PTFE parts are required to bury in landfills instead of incinerate because high temperature will result in the release of hydrochloric acid and other toxic substances. In a study in 2001, PTFE was proven to degrade environment into other substances that are harmful to plants, which was trifluoroacetate. Although the level of trifluoroacetate is not significant, it remains for a long period of time, causing pollution in the near future and also bioaccumulation in food chains. Next, another concern aspect of PTFE are the environment harm that comes from its production, use, and decomposition. An increase of phytotoxin trifluoroacetic acid or TFA was linked to PTFE. This phytotoxin is toxic to aquatic life while being much more stable than acetic acid and is harmful to all water ecology. It was found at much higher concentration in Hawaiian water despite the regulation limiting the use of hydrochlorofluorocarbons.
The primary source of non-stick properties in cookware today is a PTFE coating, or coatings closely associated with PTFE. Cookware predating PTFE were made non-stick through the polymerization of oils, fats, and waxes. This layer of fat, oil, and wax is commonly referred to as seasoning. Cast iron, carbon steel, and other ferrous metal cookware rely on a layer of seasoning to prevent rusting, but also to aid in non-stick properties. Users of cast iron, carbon steel, and other ferrous metal cookware apply a thin layer of non-saturated fat oils and wax, then expose the cookware to heat beyond the smoke point of the oil or wax. Contrary to popular belief, this seasoning has nothing to do with flavor and has no effect on the food flavor. When non-saturated lipids are heated beyond their smoke point, aldehyde groups in the lipid react with one another, forming a matrix of bonds. Waxes are sometimes introduced so that ketone groups in the wax may also react with aldehyde groups to form a more complete network of bonds. These reactions are forms of an aldol condensation reaction. The penultimate result of the aldol condensation is a plastic-like layer of polymerized fats, which has non-stick properties but is not uniformly repeating like PTFE. Generally speaking, cast iron cookware that has been seasoned well should have a non-stick surface, which will naturally reseason while cooking food. However, application of a light layer of oil is required to initiate non-stick properties. Cast iron and carbon steel cookware are currently experiencing a resurgence in demand due to consumer concerns regarding the toxicity of PTFE at high temperature and a return to more natural products not aided by chemistry. Unbeknownst to most cast iron users, the fumes generated during cast iron seasoning are similar and have similar effects to the fumes produced by PTFE at high temperature. That being said, perhaps the strongest argument for returning to cast iron and carbon steel is the lack of direct environmental impacts from their production and use.
Another application of Teflon can be found in the use towards double insulated steam wands on espresso machines. Because of the free radical polymerization of tetrafluoroethylene to form Teflon, we see a high thermal stability and low thermal conductivity, making it an ideal candidate for insulating steam in the espresso machine. Also, it's extremely inert and high melting point at 327 degrees Celsius, which we can thank the carbon-fluorine covalent bonds for. Ultimately, it adds confidence to its use in espresso machines. Now, if you ever use a steam wand with no burn technology, you can be sure to thank the Teflon tubes for that ease of life improvement. To conclude, we learned about the discovery process of Teflon, how it's manufactured at an industrial scale. Also, we learned about its controversial application in nuclear warheads, followed by the environmental implications on marine ecosystems. Then we cracked on to learn about how Teflon is used in non-stick cookware by cooking an egg. Then we wrapped it up by learning about another application of Teflon, which can be found in espresso machines to improve the safety of baristas at large.